So just quickly kind of summarize some things here. We'll all have this back up here again another time, so don't worry about jotting all this down right now. But so a quiz probably after Thanksgiving, probably on that Tuesday when we come back. To be honest with you, we'll probably spend Monday kind of wrapping everything up, kind of reviewing it. A few. I don't know about anything new necessarily, but it'll be a chance to come back and practice some more algebra limits and be like this worksheet. It'll be a chance to just kind of go over things and so forth after the break. But so we've got section 4 to talk about, but section 4 kind of comes in and combines what we've learned here with these shortcuts with the equations. And then we're just going to do kind of parts of a little bit of chapter 4, or section 4. But it kind of combines what we've been doing with the equations, these shortcuts, with the derivative rules that we learned in 2.2, with the chart stuff that we did in chapter 1. Okay? And we're going to kind of get started with that process a little bit today. So we'll have today and tomorrow to go through that. So 2.1 is where we introduce the idea of the derivative the long way, the definition of the derivative, slope between 2 points, the 2 points becoming 1, right? That's how we can do the derivative. And then that led us to, in 2.2, that led us to the shortcut way of doing the power rule. And we already know the derivative of sine is cosine. We know the derivative of cosine is negative sine. We're not going to probably do those much of that on the quiz, though. Maybe the shortcut rule a little bit, but not as far as other stuff. And then e to the x is its own derivative. We also know that if we compress the graph, that we have to kick that out. If there's a number on the inside, we have to kick that out because that's stretching the graph or compressing, making the slope steeper. We talked about some of those things a little bit in 2.2. And then, so then in 2.3, it was like, okay, if derivatives use this idea called a limit, maybe we should take a little side trip. So 2.3 is a little bit of a side trip to say, well, let's talk about limits. And so that's probably the hardest part of the quiz for some of you, I know, is looking at your worksheet there, the algebra component of it. But, you know, we're going to got to practice that. And so if we're going to do limits, just limit problems. So again, a little bit of a side trip, doesn't really necessarily have to be about derivatives. It could just be a limit problem. And a limit problem is just saying, what is this output approaching as the input is approaching, you know, whatever. Okay, so how can we do that algebraically? We can factor and cancel. It looked like people were doing a pretty good job with that, but the common denominator bow tie one we struggled with, looks like a little bit the conjugate one. And then, of course, direct substitution probably should be at the top. That's the first thing you do. Today, we're going to talk a little bit about how you can use the tables on your calculator to investigate limits a little bit. So we're going to do that a little bit today. And then, of course, your book homework was looking at a graph. I think this is the easiest way to do limits. Were the ones in the book, right? The ones with the graph. That's pretty easy to look at those. And so we can do limits that way. And then when we are doing limits algebraically, I've kind of got this off to the side. What do? Well, we try substitution. And sometimes when you do substitution, you get an answer right away. Like there'd be a real easy one. Plug in a 2. 2 plus 3 is 5. There's your limit. Real easy. Okay, but most of the time what happens, that's why this blue check mark's here, most of the time we get 0 divided by 0. And that's called indeterminate. We can't determine if there's a limit or not. There might be, probably is, but we have to keep going. And so what do? We do one of these things over here, right? We do one of these things over here, and we find out what that is. But if you get 6 divided by 0 or 2 divided by 0 or something like that, at this point we'll just say it does not exist. So when you substitute in, if you get that. Okay, so most of our limit problems are going to be in this realm right here. 0 divided by 0, and then we keep going, do some algebra, and then we can plug in and get an answer eventually. So that's 2.3, and then 2.4 is just, like I said, we're going to come back and bring our chart stuff back in from chapter 1, except we're going to do it with equations. So we're going to look at local max, local min, inflection points. We're going to do a little of that today too. You know, stationary points, maybe inflection points, concave up, concave down, that kind of stuff. Okay, so that's it. I mean, that's kind of where what things will be that we're trying to do here. Again, the hardest part of what we do, a big part of the quiz, and this stuff we probably have to spend some time on, is this idea of the limit. But remember, the reason we're doing the limits is because the definition of derivative, this major idea in calculus that we're dealing with, involves a limit. So we need to study this idea of the limit. Okay, so let's do the easiest limit problems there are, and that's the ones in your book here, like on 13 through 26. So this is where you just think, okay, do the cars meet, right? Remember, the whole idea of a limit is what are the x values, what are the y values approaching. So right here, what as the x, here's the y values, so as the x values come in here towards -2, what are the y values approaching? 0. That would be your limit. Okay, right here, as x approaches -3 from both sides, as x approaches -3, what are the y values approaching? -1. That would be your limit. Even though the diner has burned down, there's a hole there, doesn't matter. Those y values are coming in towards -1. So I want you to think about this is when we use our calculators here a little bit. Okay, what about here? As x approaches 2, what are the y values approaching? Y values are approaching 1. The cars are coming in at 1. Doesn't matter there's a hole there, and it doesn't matter there's a dot down here. The limit as x approaches 2 is 1. But what if I ask you what's f of 2? What would you say? You would say -1. F, that's a different question. F of 2 says what's the function output at 2? Well, the function output at 2 is -1. Okay? But the limit is a different question. The limit is where are the cars meeting? The cars are meeting up there at 1. That's the limit there. Okay? So any questions on 13, any of those I didn't address there on 13 through 26? Any of those that you had that you wondered about?
You explained that to basically.
Oh, the little plus minus sign? So like, give me an example.
I think it's 16.
16 and 17. So 16 says the limit, yeah, good question. The limit as x, I kind of forgot about that. X approaches 2, what does that little minus mean? From the left. So the little negative sign means from the left, the little plus sign means from the right. Now, those will never be a does not exist answer. The car is approaching somewhere from one side, okay? But from both sides, they might not. So like, for example, right here, right? The limit from the left is, now this is not this one, I know. The limit from the left here is what? 1. So this y value is approaching 1. From the right, it's approaching 2. Not only approaching, it is 2, but whatever, it doesn't matter. So the limit is approaching 2 on the right. On the left, it's approaching 1. Here we would say, though, what would you say then? I don't know which problem this was, but what's the limit as x approaches -1? Does not exist. The limit from the left has to be the same as the limit from the right. So limit from the left is 1, limit from the right is 2. Okay, so the limit itself doesn't exist. So back to this question. As x approaches 2 from the left, well, as x approaches 2 from the left, what's that approaching? The y values are approaching 1. So that's the limit, right? And then 17, I think, was what's the limit as x approaches 2 from the right? Well, what's x as x approaches 2 from the right? As you come in this way, the y values are approaching 1. So here you get 1, here you get 1. So then the question is, what is the limit as x approaches 2? Right? 1. Because the limit the two cars meet, right? So the question is from the left or from the right, they're just saying, where's the left car going? Where's the right car going? If they come to the same place, that's the limit, right? That's the answer to as x approaches 2. If they're going to different places, then we say the limit does not exist. So at -1, where we have this break, we say the limit does not exist. Cars aren't meeting. Okay? What else, sir? Anything else on 13 through 26? about the ones that say f prime at the end there? Then what are you looking at? What are the slopes approaching, right? So the limit of f prime as x approaches 3. So as x approaches 3, you'd be saying, okay, what are the, you're not talking about these y values, now you're talking about these slopes. Well, what are the slopes on the left side of 3? What's the slope of this line right here? -1. So the slopes here, they're not even changing, they're -1. So the slopes on this side are -1, slopes on this side are -1, so the answer would be -1. So that, again, it's just the outputs, right? That the idea is it's what are the outputs approaching as x approaches 3? Well, the outputs of that are the slopes of this graph, right? So to the left of 3, slope -1, slope -1, slope -1, slope -1. On this side, slope -1, slope -1, slope -1. They're approaching the same thing, -1. Okay. So that's what was going on there. All right. What else do we have in book 39 through 42? So that would just be a matter of so on 39 through 42, you could graph those, right? You could graph you could graph that piecewise function, but you don't really need to, because in a piecewise function, so go back to this right here. Okay, this is clearly a piecewise function, right? So if I give you an equation like 39 through 42 that's a piecewise function, where's the point of interest? Right away, right? What draws your interest right away? When x is what? On 39 through 42, should have your book open, probably. Okay, what x coordinate draws your interest on that section? Yeah, when x is what? If something strange happens on that piecewise function, on 39 through 42, am I looking at the right problem? At 2, right? When x is 2, because what's happening when x is 2? What's happening with this graph when x is 2? It's changing equations, right? It's changing equations. Just like here, we got this line until here, and then it changes to this, and then it changes to this little curve thing, and then it changes to this. So right away, when you see a piecewise function, the interest here is at 2, right? Because when it changes from one equation, so what's the first equation before x is 2? What kind of graph is that? Parabola. Now, is that going to have any problems? I mean, where are the weird things here that worry you about the limit not existing? It's when there's breaks or gaps or jumps or something, right? Was there going to be any gaps in a parabola? No. So to the left of 2, there's going to be no deal. So there's going to be no problem. So it'd be like this, right? The y values are going to be whatever the y value is, that's what the limit's going to be, right? The only time the limit gets weird is when you get a hole or you get a break, right, or something like that going on. And in a piecewise function, that's where it breaks, is at 2, right? You can tell. I mean, you just look at the equation, piecewise function, you can tell where the weird stuff's going to happen, which switches from one graph to another. That's when you're going to maybe get these breaks. So to the left of 2, we can just plug in and get our limit. And then to the right of 2, what kind of equation is it? It's just a line, right? So after 2, we can just plug in, because that's just going to be a basic thing. So the only limit problem on 39 through 42 that would be remotely interesting is at 2. So on 39, it said, what's the limit as x approaches 3? So you're going to plug a 3 into what? The line, right? Because that's the part of the graph that's after 2, right? So x approaches 3, so 9 minus 5, 4. You're just going to get that answer. It's all good. So you wouldn't have to graph this. If I gave you this problem in a quiz, I'd probably put an XY axis there and say, hey, draw a graph if it's helpful, right? I mean, already in chapter 1, I made you graph a piecewise function, but you probably not going to make you graph one, but I might give you an XY axis and say, hey, draw a graph, or just not even give you an XY axis. I might say, hey, draw a graph if it's helpful. But I don't think you need it, okay? As x approaches 0, what are you going to plug a 0 into? The parabola, because that's what this graph is when x is less than 2. So you plug a 0 into the parabola and you get 3. Okay? And then, let me skip 41. And so 42 says when x approaches 1. So where are you going to plug that into? You're going to plug that into the parabola, right? And whatever that y value is, what you're going to get, because there's not going to be any weird things going on in the parabola. The only weird thing, the only break or gap or something strange happens is going to happen at 2. So that's where 41 gets interesting. So then what would you do on 41? If you haven't graphed it, what would you do to check the limit at 2? Put it into both, right? Put it into both. Put it into this one and see what you get. Put it into the other one and see what you get. And if you get 2 different things, that's bad. Right? Limit's not going to exist because that means you got that break. But it might be that when this one stops and the other one takes off, they might do it at the same place. So if they do it at the same place, that's where the cars are meeting. So we plug a 2 into the first one and we get 1. We plug a 2 into the second one, and we get 1. There's our limit, right? So our limit's going to be 1. If we were going to graph those, the parabola would stop at the point 2,1, and the line would take off at the point 2,1. And that's where the cars would meet. Okay? It's just like that little video we watched the other day. So when you got a piecewise function that's a parabola turning into a line, when the parabola stops, the line's either going to take off from there, or it might take off from up here. If it takes off from up here, then you don't have a limit. The cars don't meet. Limit doesn't exist. But if the second graph takes off where the first one ended, then you got a limit. Okay? The cars would meet. All right, so that's just a lot of different ways to ask these same questions, right? So, back to what we were saying as far as things we're learning here. So, graphs, pretty easy to do limits, right? Do the cars meet? Okay, so now let's talk about this algebra, all the algebra stuff. That's probably the stuff that some of you are going to struggle with the most. But whatever, let's go take a look at that that page. Okay, so what did we get on? So the first 4 we seem to do pretty good on. Okay, on this one we plug in a 2. We get, I think we get 0 divided by 0, right? So you do some canceling, and then you end up with what? How much? Negative 3/4. Okay, on this one, you plug in a -1, you get negative 2 divided by 0 right away. So we say does not exist, right? Does not exist. On this one, we plug a 5 in, we get 0 divided by 0, right? So then we factor and cancel it, and then after we cancel that, we end up with what? Like an x plus 7 over an x minus 5, like that. And then we plug a 5 in, and we get 12 over 0. And so what do we say? It does not exist. So you get 0 over 0, you keep going, do some algebra to it, right? Okay, this is just a way of, when you don't have a calculator, you can't see the graph of this thing. But again, what could we do if we wanted to look at this problem right here? If we had our calculators, we could graph that right there, and that would turn it into the problem we were just looking at, right? Matter of fact, let's do that. Now, I don't think you can log in yet. Let me start this. Okay, well, we'll come back to that. We'll come back. I'll get this started. You guys can log in, and we'll talk about these worksheets. But what we want to talk about today is what if we could use our calculator? Well, we could draw a graph, and we could look at it, and it'd be like one of those easier ones, right? Now, we're going to look at the table, because a table gives you the y values. And what we care about in limits are what are the y values doing. So the graph could do it. We could graph and trace, but we're going to do the table, because the table is just like tracing. It's just putting it into a table. Okay? All right. So, okay, should be able to log in here now. So, going back to here. Okay, so that was undefined. So now here on this one, you put a 2. This is where you want to make sure you don't forget about substitution, because some people would start to cancel, factor and cancel this. Turns out it's okay if you do, but it's unnecessary. Okay? So here you put a 2 in here, you get what? 20 divided by 4, you get 5. Did I do that right? Did you get 5 on that one? You just get 5. Boom, you're done. There's your answer. Okay, so I'm not going to spend a ton of time on this. Some of you came in earlier to get some help on this, and so if you need some help, you can come in and see me. But we talked about the conjugate method, so wherever you see the radical like that, you multiply that. Well, that's going to give you this on top, and that's going to give you this on the bottom. I'm not going to waste your time with this a whole bunch here. Now, those will cancel, kind of. What do you got to do with the 9 minus x? you gotta take out a negative, right? Take out a negative, that'll turn the 9 negative and the x positive, which is what you want. So let's factor out negative, then those will cancel, okay? And there we got it. Now we can put our 9 in, square root of 9 is 3 plus 3 is 6 with a negative, so we got negative 6. So that's the conjugate method, right? You got a radical, be thinking about doing that. Here we got a radical minus a radical, so I would do radical plus a radical. And I would do that over here as well. Okay, now I'm not going to do anything to the top, but what happens when I FOIL this bottom? Radical times radical would just be x squared plus 12. Outers and inners drop out. That's the whole point of doing a conjugate. And then what's root 12 times root 12? 12 with a minus, right? Because there's a negative bottom. So look at that. So the whole bottom ends up being x squared, right? And then what do you got on top? You got that times that. Well, what can you do with the x squared? You can now cancel the x squared. And so all you're left with is this guy right up here on top. Now you put in your x approaches 0, you get 0 plus 12, so you get root 12 plus root 12, that'd be 2 root 12. Which I'm fine with you leaving that, but you could simplify the root 12. Okay, so those two are exactly the same problem. Okay, just when you see the radical, you just got to multiply by the conjugate. Multiply by the conjugate. Okay, we talked about getting a common denominator. This is a little different than the one we did in the sense that it's not a fraction inside of a fraction, but it's still, you got to get a common denominator. So we bow tie. So inside the parentheses here, we're going to have 5 minus x. That goes on top, that times that. And then minus, and now I do 5 plus x times 1, so I better put that in parentheses. And then that's all over what? The two bottom ones multiplied. There's your bow tie. Remember, your bow tie always goes here, then it goes here, and then it goes there. Right? That's your bow tie. That's the bottom. So that'd be 5 plus x, 5 minus x. Okay, so that's all that, and then this, of course, is just still hanging out. Now, some nice stuff should happen on top. What happens on top here? I get 5 minus x minus 5 minus x. So all that becomes what? No, it's not 0. It's negative 2x. And then I got this 3 out here. So that'd be negative 6x on top. Right? And then the bottom is going to be an x, and then a 5 plus x, and a 5 minus x. Right? So 5 minus x minus 5 minus x, that's minus 2x. Times a 3 is negative 6x, and here I got an x times the bottom. What can I do with those x's? Now I can cancel those x's, and that's a good thing because I want to let x go to 0. So now I can put a 0 there, that'll be 5. Put a 0, that'll be 5. And on top I got negative 6 over 25. Negative 6 25. Now, but you just got a bow tie, so you got to take that times the 1. Well, excuse me, do this one first. So 5 minus x times the 1 is that. 5 plus x times the 1 is that. You subtract them. And then the bottom is those two things bow tie. Okay, and then my suggestion on this would be to FOIL this out. And if we do it with Pascal's triangle, it would save us a little time. So this would be 2 cubed, which is 8, plus 2 squared x, so that'd be 4 x. And I forgot what I forget on Pascal, 1, 3, 3, 1. So I need a 3 on this, so this would be 12x. Okay, plus, and then I got another 3, and then I got 2, so that'd be 6. X squared, and then plus x cubed, and then minus 8. I think I did that right. But you got to FOIL it out, okay, because the nice thing that's going to happen is those 8's are going to cancel. Okay, what can I now do? Now I can factor out an x on top. I got 12 plus 6x plus x squared, all over x, cancel, cancel. Now I can put in my 0. What do we get? Okay. That's actually a lot like the derivative ones we were doing. Take that x out of there and replace it with an h, right? Take that x out of there, think about that now. Take that x out of there and make it an h. It's the same thing we did with our derivative when we did the long way. So we'd FOIL that out, these would cancel, that was nice. We could take out an h, but this is going to go to an x, and there you go. Okay? So, we'll have another opportunity to practice that, but I've got a sheet online, I think, that's some extra practice on conjugate and stuff like that, so I'll show you that if you want. Need some extra of that. So there'll be a section on the quiz that'll look a lot like this sheet right here. There'll be a section of problems that look a lot like this. Okay? Some easier ones, some factor and cancel ones like this up here, and some of the bow tie conjugate kind of situations there. Okay, so if we think back to what we talked about here, right? So what did we just go through? We went through some factor and cancel. We went through a common denominator cancel. We went through conjugate and cancel. We had some that are substitution. We've also went through some graph ones on our book homework, okay? And those are the easy ones, and you like those because you can just see where do the cars meet, that kind of thing, okay? So now let's get out our calculators, and let's take a look here. So let's... Harish, how do you say this? All right, so let's take a problem here that we've done recently. So you can just put this in your notes somewhere in the back of your worksheet. I don't care where we're going to do it. Here's a problem we did recently. Okay, right here. Okay? We want to do this limit problem. Now, what if I gave you this, and so let's, all right. So let's look at this top one here. And so if you were doing this no calculator, what would you do right away? First second, what would you do? Top one, you plug in a 3, what do you get? 0 over 0. So that tells you to what? Keep going. Now this one's an obvious one. What are you going to do? You're going to factor out an x plus 3, x minus 3 on top. You're going to cancel an x minus 3. And so this thing's actually going to simplify down into x plus 3, right? Because the x minus 3s will cancel. And so then you're going to get what for your answer? 6. Okay. Now, so that's the algebra one. Easy algebra one. That's the algebra way of getting that the limit is 6. Okay? But another way to do this would be, what if we had our calculator? So everybody get your calculator out. And I want you to take this right here, and I want you to graph that. Okay? Because what if we get one where that thing there doesn't, there's no algebra we can do to it, right? What would happen if there's no algebra we can do to it? Well, we have to think of this another way. We have to graph it, okay? So we go onto our calculator here, and Harish is doing this for us, and you guys can do it right along with us. And we graph it, say, ah, that's interesting, looks like a line, that's strange. I wonder, oh yeah, sure, it's a line. It's the line what? It's x plus 3. Except that, trace at 3, Harish. Trace at 3. What's going on at 3? Menu, trace. What's going on at 3? There's a hole there. There's a hole there, right? This graph is not defined at 3. There's a hole in that. That is not a vertical asymptote, right? There's a hole there. But what's the limit? Still 6, but now how could you tell? Because when you look at this, you can't tell that it's 6. So Harish is in trace mode, so just go to the left a little bit, Harish. Go to the left just a little bit. 6.3. Now go to the, that's the right, but your other left. Okay, there you go. Go to your left. 2.4. Okay, go back. We don't go way down there. We only really care about where? At 3. We care about right by 3. So there's 5.7. And then at 3, it's no good. And then Now, 2.7 is not very close to 3. What would be better? How about 2.99? Okay, how about we go 2.99 and trace? Oh, okay, 5.9. So now I'm getting a feel for, I'll bet those cars are meeting right there at 6. I'll bet they are, right? Now, so you can do it with a graph, right? So we can do it with a graph, and we can kind of see. But what we really care about are those values, right? Those Y values. So the calculator has a table feature, so we're going to do this, and there's going to be some on the quiz. I'm going to put on the calculator part of the quiz where I actually want you to write down the table on your paper as your answer. So we're going to do that right now. So go to your table. Now, there's a couple different ways to get to it. The quickest way, I think, if you hit Control T right now. I think if you hit Control T, okay, you'll get a picture of this table here. Okay, now hit Control T again. And then it goes away. Go under Menu to Table. And yeah, see, I think our only option is a split screen table. So go ahead and hit Table. That's fine. Okay, Control T, right? And now, what we want to do here with this is we want to change our settings on our table. Now, notice that the table has a black thing around it here. Like if Harish went over here with your trackpad, go over here with your trackpad. If you clicked over here, okay, just click in there. Now see how the graph is black. So now all your menu items are for your graph now. So go click back in the table. When you hit Control T and the table comes up, the table's active. Okay, so now we're going to go to Menu and Table. Now notice how Menu looks different now. So we're going to go to Table, and now we're going to go to Edit Table Settings. Okay, we're going to go to Edit Table Settings. Everybody's got to be able to do this now. Okay, so Control T will give you a table. Because now, again, it's just like tracing, and we're trying to see where the cars are meeting. Now, we care about 3, so we want to put 3 right in the middle. We want to look at both sides of it. So we're going to start our table at 3. And I'd say we want to do our table step, I'd say at least 3 zeros. So probably not more than that because we're not going to have room to see a whole bunch. So let's go 0.0001. So we want our table to go by these small increments. Okay, hit enter. Leave the rest of them as auto. That's okay. All right, see that now? Okay, now arrow up. Arrow up a couple. Yeah, get 3 right in the middle. Okay, see how we got 3 right in the middle? Now, do we care that it's undefined right at 3? That box, that cell that Harish has highlighted, I could care less about that. I don't care what's there. It doesn't matter. It doesn't matter. What matters are the Y values on each side, because isn't that what's telling you what the cars are doing? Car on the left is up here, 5.99999, the car on the right. So this is obvious evidence that the limit is what? 6, which we already had algebraically figured out was 6. But now, what have you got when you can't do algebraically? The table could give us a good look. So this is investigating the limits. Now, sure, we got this nice calculator that just do limits for us. Why not do that? But that's lazy. Okay, plus, we're not learning anything there. All right, now, I want to ask you this question. What if I would have given you the question this way, though? Is that the same? Is it the same question? It's the same exact question. And so is this, same exact question. Well, how could you use your calculator to graph this? You just have to change the A's to X's, right? If you want to do that limit and do it by graphing, you can't graph with A's, you have to graph with X's, right? So when you went to your calculator to put it in, you would have had to put x squared minus 9, x minus 3, like we do, right? So just understand that. Now, why do I say that? Well, what's the first limits we learned about? The first limit we learned about said what right here? H approaches 0, right? The limit of the derivative was H approaches 0. So if we were going to do one of those on our calculator, we would need to not put H's in, we need to put X's in. Okay, matter of fact, let's do one of those that we already know. Let's do one. We know, let's use our calculator. We know that, let's pretend I had f of x equals x cubed. Oh no, that's too crazy. Let's do, how about this? F of x equals x cubed, and we wanted to find f prime of 3. Let's say we wanted to do that. Now, you know what? We already know how to get the answer to that, right? Because we already know a little shortcut. What's f prime of x for 5x squared? 10x, right? We already know that. That's our shortcut, right? If f of x is 5x squared, we already know that f prime is 10x. So what's f prime of 3? 30. So we know f prime of 3 should be 30. But you know what? Let's go old school. Old school was like 3 days ago. But let's go with our limit definition. So everybody write this down. So this would be the limit as h approaches 0. Because you know what? You're going to do this on the next quiz too. I'm going to say to you, hey, here's a function. Here's a function. Set up a derivative to find f prime of 3. And then use your calculator, using the limit definition of the derivative, set up an expression for f prime of 3, and then use your calculator to figure it out. Okay? You with me? Okay? So, let's do one we already know the answer should be 30. Okay? So what would we do? We'd set this up and we'd say, okay, f of, this is all good review right now. F of what? Not x plus h. Not for this one, since I'm doing 3. 3 plus h minus f of 3 all over h. Remember that? Right? This is just the definition of the derivative. So we're going back to before we had learned about these shortcuts. Okay, now what do we do? What do we do for f of 3 plus h? Plug that into our function. So we have 5 times 3 plus h squared minus, and then we plug a 3 in. What's that? Plug a 3 into f. That's 45 all over h, right? Now, this happens to be one that we could keep going and work it out, right? We could keep going, da-da-da-da-da, and you're going to have something like that. On the no calculator part of the quiz, you're going to have some we got to work out the long way. So I'll say, okay, here's f of x. Use the definition to find f prime of 3, right? And this is what it would look like, right? Right? I mean, not quiz isn't today, right? But f prime of 3, and so that's what we would do. We'd set up the definition of the derivative. We would plug it in like this. But now let's stop right there. Instead of going and using our algebra, this would be our factor cancel stuff, and we could work it out and find it. Instead of using our algebra, let's go to our calculator. Okay? So we're going to put this in, the red thing, into our calculator, except we can't use h. We got to use what? We got to use x, right? Like the example we were just talking about. Okay, so we're going to put this into our calculator. Not this. This isn't the function we're putting in. This is what we're putting in, because we're trying to do the limit of this as the x's are getting close to 0. See how I changed that h to an x already right there? Okay, because that's what we're going to put in. All right, so Harish, you already got it? Here's what escape. Here's what I would do. Okay, I don't know where you're at here. What'd you do? Oh, you cleared everything out? Oh, that's fine. Whatever. You could have just went and edited the expression in the table. You just could have went to F1 and redid it, then your table better. That's fine. No problem. Okay, so let's put it in. So we had a fraction. Yep, we had 5 parentheses. That was 3 plus h, I think, right? Yeah. So this would be 3 plus x. And it was squared, wasn't it? Wasn't it squared? Divided by x, right? We're changing the h's to x's so we can graph it. Okay, here's this graph. I don't really care about that. I don't really care that I can't see it. I don't need to set my window because I'm going to go to a table here, right? Now, where do I care? Where am I trying to look, really? At 0, right? Now, you could trace at 0 right now, but that's kind of wasting time. But for investigating, it's not a bad idea. Trace at 0 right now, just for the heck of it, Harish. Trace at 0. Okay, it's undefined there. Go to the left just a little. Arrow to the left just a touch. Look at that, 28.5. Arrow to the right just a little. Okay, 31.5. Now, what did we say our answer is going to be? 30, right? So it looks like we're in the ballpark. Whatever, hit Control-T. Let's go to our table, because what I want you to put on your paper for this problem is this table. You actually copy the 2 columns of your table. Okay, so now where do we go once we get the table in? The settings. So you go to Menu, Table. Where do we want to start? 0. Now the other one we started at 3 because it was a limit as x approached 3. Now it's a limit as x approaches 0. And then here we always put in 0.0001, right? Because we want just to have right? And there's our table, and now arrow up a couple. Now this is just scientific notation here. Okay, now you can usually see on your table, you can usually see 2 on one side and 1 on the other. We don't care that that's undefined there. We don't care a lick about that. But clearly there's evidence that says our limit is what? 30. So on your paper, I would rather you not write this notation. I probably can't wrong. But really what that is negative 0.0002, and this is negative 0.0001, and this is 0, and this is 0.0001. Okay, and then you jot down this, put undefined, you just copy this table, just this part right here, put that right on your paper, and then that would be evidence that, okay, 30 is our limit, right? Which, of course, we knew was going to be the answer. But now let's take one real quick that we don't know. So now let's say I gave you the function f of x equals, I don't know, tangent. And I wanted you to find f prime of 3. Right? We don't know the derivative of tangent. We don't know a shortcut for tangent, do we? So I say, well, set up a limit for that. Okay, let's do it. Limit as h approaches 0, f of x plus, not x plus h, I made the same mistake. F of 3 plus h minus f of 3 all over h, right? And so now we do what? We'd say, okay, let's plug that in. So again, the question on the quiz might be set up a limit using the definition of the derivative to find f prime of 3. Set up a limit using the definition of the derivative to find f prime of 3. That's what we're doing right now. So what's f of 3 plus h? Tangent 3 plus h minus tangent 3 all over h, right? And now we would take this part and we would put it into our calculator. Now there's no algebra we can do there. Now some of you are thinking about distributing that tangent. Shame on you. That's not multiplication. There's no distributing of that. There is some rules of how you could do a sum, a tangent sum, sine sum formulas. You guys worked with them last year when you were doing identities. But you can't distribute that. That doesn't work. Okay, so there's just no algebra we can do with this right now. There's nothing else we can do. Okay, we don't know the derivative rule for tangent yet. Okay, we will, but we don't right now. So the only route we have to find out this limit is let's put in our calculator and let's see what these outputs are going to when the input h is going to 0. That's all we're doing. Okay, so Harish has got it graphed there. Okay, and if he traces at 0 right now, something we're going to get undefined right there, but if he goes to the left just a little, if he goes to the right just a little, that was the right, go to the right, whatever. Go to the left, right. What's it look like it's approaching? What's it look like the cars are meeting? Looks like the cars are meeting at 1. There's a hole there. It looks like the cars are coming down, the one on the left, one on the right. Looks like they're meeting at 1. Let's go to your table, hit Control T. Again, we're looking when x approaches 0. So go to your settings. We want to start at 0, 0.001. Arrow up. Pretty good evidence right there that those cars are meeting at 1. On both sides of 0, they're coming in and getting close. It looks like the 1. Now you might say, is it 1? Maybe it's 1.02 something. Maybe it isn't 1, right? How could you investigate that a little more? I'll be honest, it really isn't 1, actually.
You have to go smaller.
We got to go smaller increments. So what you could do, if you weren't really convinced right now we only have to be accurate to how many decimal places? 3, don't we? So go ahead and go. So if my 4th and 5th decimal place weren't changing, I'd feel pretty confident I was already there. So go to your settings. Let's add another 0 or 2, maybe 2 more zeros. Okay. Now you got to make sure you put this back to make sure you put that back to 0. Okay, put that back to 0. Now we can put 5 zeros in there. Okay. Oh, see, yeah, it isn't 1. So it looked like it was 1, didn't it? But it isn't. It's like it's actually tangent of, well, it's not tangent of 3. It's like secant of 3 squared or something like that. But it's really, 3 is really close to pi, right? So that's why we're getting something really close to 1, because pi would have probably given us 1. Okay, so now I would put 1.020 as my answer if I was doing this one. Okay, all right. So now what does that mean? What did we just find? Well, what we just found is that the tangent graph, the slope at 3 is about 1.020. Right? So it's just different ways of looking at these limits. Again, keep in mind, all we're doing is saying what, again, go back to what I told you a limit's all about. What are these outputs approaching as the inputs are approaching this? So by graphing this and looking at a table, we can see what the outputs are approaching as the inputs are approaching the 3. So that's just a way to do this with tables on a calculator. Okay. Yeah, I trust you. I know what's going to happen. You guys are going to be going there, not going to pay attention to anything else I say, because you're going to be working on this, because you're going to want to get it done. And that's not good. All right, so I put together, now there's 2 sides to this. Ignore the back side for right now. We'll do that another day. So just the side that says calculator limits. Okay, so very first one there. Okay, very first one. Let's go through and let me just show you what I want you to have here. Okay, so we're going to go onto our calculator. So everybody, let's get onto our calculator here. Okay, so we're going to graph that thing into our F1. Now, we can do that one with the conjugate method. Okay, matter of fact, while you guys are doing that, I'll do that. Now, the stuff you see in red is not anything you would put on your paper. The blue is what I want to see on your paper. But we could have done this one by the conjugate method. Okay, I FOIL that top up there. I get x plus 1 minus 1. The bottom would be x, and then all this. So while you guys are graphing on the calculator, I'm going to put this down here. The 1's cancel. Then my x's would cancel. And I get 1 over the square root of x plus 1 plus 1. Now I put a 0 in right there. Square root of 1 is 1. 1 plus 1 is 2. I get 1/2. So what you see in the red and the black, don't put that on your paper. But I'm telling you, that could have been on the algebra one. That could have been one we do with algebra. And I just got 1/2. Okay, Harish, tell me what you're getting in your table. Now, across from the 0, I'm assuming we get undefined. Oops.
0 is undefined. -2 is also undefined.
Why would -2, why would I care about -2? Did you go into your table settings?
Oh.
You didn't go into your table settings. -2 is undefined because you can't have a negative inside the square root. So this would be 0.0001. This would be -0.0001. This would be -0.0002.
And for 0.0001, I mean 0.49998.
This one right here?
No, for the 0.001, the positive one.
This one is what?
It's 0.49998.
Okay, and this one is?
That one is 0.50001.
And this one is?
0.50002.
Like that. The blue is what I want to see on your paper. And then the answer right here is clearly 0.5. There's clear evidence there, clear evidence that these outputs, the y values, are coming, on both sides, are coming towards 0.5. The outputs are approaching 0.5. So we had a graph of this at 0, right? That thing would be coming in at 0.5. Okay, actually this one. On the right it's below 0.5, and on the left it's above. So the cars would be meeting here at 0.5. Even though the diner is burned down, that's this column in there. I don't care about that. Now, sometimes there might be a 0.5 there. That's fine. So every one of those on this page, I want you to have that table. Something like that.
The expression that we've just did, that's only for the test, right? Not for the expression.
Say that again?
Like, you know how you said that we've tried the expression or whatever? Is that just for the test?
Well, see here I just give you the limits.
Yeah.
I just give you these and have you do it. But I might say, use the definition of the derivative, the f of a plus h minus f, to set up a limit. And then use your calculator to tell me what the answer is. And then that's when you would go to this. Make sense? Okay? So you need to have, to help with your understanding of limits, you need to look at them in a variety of ways. Understand that we can solve them by doing some algebra like I did in the red. We can look at them graphically. They're easier to look at graphically over the table. We can see those y values. That's all we're doing. So if you really understand the idea of limit, you can look at it in all these different various forms and still make sense. Okay? All right. Now, like I said, now I know you're going crazy and you want to get that all done. But let's set that aside just a little bit, if you would. And let's turn in your book. And page 114, page 115. Okay, so we've kind of exhausted the idea of what we can do with limits. Now, again, needs some revisiting. You need some more practice on common denominator, stuff like that. That's fine, and we're gonna get that. That's one of the things we'll come back and work on Monday, probably. Or I may give it to you tomorrow and have and then we talk about it Monday. We'll see. Okay. All right. So shift gears here a little bit now, away from the limits. Remember that was kind of a side trip. Let's come back to the idea of derivatives and the chart and those connections, f prime, all that stuff. Okay? So, we all understand that if I have f, a function f, and I do the derivative of that, that's f prime, and I do the derivative of that, that's f double prime, right? So going this way, I'm doing the derivative, correct? So f double prime is the derivative of f prime, and f prime is the derivative of f. What would we call it? So this would be doing the derivative, I guess you might say, going this direction, right? Doing the derivative. Take the derivative of something. So we go from f to f primes, doing the derivative, going from f prime to f double primes, doing the derivative. So what are we going to call it if we go the other direction? Well, look on page 114. That's called doing the anti-derivative. Okay, now we just bring this up now to introduce this notion. Okay, it's very simple. It's just in reverse. Okay. Now that brings some new notation. So we talked about doing the derivative of f, the derivative of f prime, derivative would be f double prime, which would be f triple prime, and we could go on and on and on. But what about this? What are we going to call I mean, because f's just a function, just like f prime's a function, f double prime's a function, right? It's just a function. So what are we going to call the antiderivative of f? Big F. Now I noticed some of you on our last quiz, when you were writing f, like your function f, you were using a capital F. So now you're going to have to be careful, because big F has meaning for us now, as opposed to little f. Big F is the antiderivative of little f, which means big F prime is what? Big F prime is, no, it's just little f. Big F prime is the same as little f, because remember we said going this way is doing the derivative, right? Going this way, going down, is doing the derivative. So if big F's up here, if it's the antiderivative of little f, when you do the derivative of big F, you get little f. And then little f prime and so forth. Now, so the question could be, what's the antiderivative of big F? Great big F? No, we won't do that. Yeah, we won't. Because usually we define a function as like little f or little g or little h. And then we just want to know there's one antiderivative. We can go one more and we'll call that cap. Now, why do we bring that up? Well, you'll see there'll be a variety of reasons as we go through this. Why? When we go to our chart, that's why I left this blank off to the side over here. Because this column right here could be big F. And then what's this row? Little f. And then f prime, right? And so forth. So it depends on the problem you're working with. Okay? And what's going to happen, a part of your homework today, it's nice review of the chart and things that were on our last quiz, which hopefully we'll get a look at tomorrow. But I may wait till next Monday. I don't know. I may wait on showing you those. But everybody's taking it, so if you wanted to come in and see, like, before school probably is about the best time. If you wanted to come in and look at yours, because I may wait on that because it'd be a good chance to review all that chart kind of stuff by going over it at a later time. But if you really want to see what you missed or something like that, you want to come in before school or something, I'd show it to you. But there's going to be some homework problems where they're going to give you a little f graph and they might ask you questions about big F. Well, isn't that like what we were doing in chapter 1 where they give you an f prime graph and ask you about little f, right? They give you an f prime graph. And just like we had already said, f double prime and f prime have the same relationship as f prime and f. And now little f has that same relationship to big F. So they're all the same questions, right? It's all the same stuff and it's all about local maximum and increasing, same thing. So it's just notation. It's just notation. So it's one more level on there. But as far as how the chart works, it's all the same stuff. So little f changes from positive to negative. That means big F would have a local max. Right? Little f changes from positive to negative. That means big F would have a local max. Okay? That's all that means. All right. So I want you to see that notation because you're going to have a few homework problems to do that. All right, let's take a look. Let's turn to page 121. And let's do this problem right here. Okay, number 19. All right, number 19 says, okay, you got this. Answer each of the following questions about the given function. Express your answers exactly. For example, square root of 3 rather than decimal form. Whenever they say that, they're really saying this is no calculator. Do this as a no calculator. Okay, where is the function increasing? Where is it decreasing? Where does it have local max? Where does it have local min? Okay, so what would this look like as a no calculator? So this is where we go into section 2.4, and I showed you this earlier. I said that section 2.4 is when we bring our chart stuff in, but now with equations as opposed to graphs. Okay, so that's what this question 19 is representing. Okay, so, well, where are we going to look for when f is increasing and decreasing, and where does it have local max, and where does it have local min? When you had a graph of f prime, what did you look at first? When f prime was 0. Exactly. Well, now what we have to do is, without a graph to do, we've got to actually solve that. So, you're going to hear me say this a lot this year. If you don't know what to do, if you're doing a chart problem, you know what to do. Do the derivative and set it equal to 0. Do the derivative and set it equal to 0. So that's what we're going to do right here. So f prime of x equals, and this is good practice now on those shortcuts we were talking about. What do you got? 3x squared minus 6x, and then this goes away, equals 0. Do the derivative, set it equal to 0. Because that's what we're looking for. We're looking for those stationary points, right? Because that's where all the interesting stuff happens. Now, how do we solve this? There's no calculator. Let's factor out a 3x. We can just factor out an x. That would actually be okay. That leaves me x minus 2. So either x equals 0 or, now what I just find then? What are those called? Roots, but what else? Those are stationary points right there. What I just found is where f prime is 0. I just found my stationary points. Now, again, let's compare this. Let's compare this to what we were doing when we were doing graphs. This is obviously a parabola. It looks like, now don't draw this. I wouldn't expect you to draw this. But basically, once I had my f prime, if this was a calculator problem, I could graph it, because this is what we're used to. This is what we did in the last chapter. Here I've got it as an equation. Well, when we had it as a graph, remember what we did then? We said, okay, it goes from positive to negative, then it goes negative to positive, right? And so we knew what? What is this right here? Local max, local min, right? We had all that. But see, now we don't have a graph to look at. Now we don't have a graph to look at, so we need to recreate that without the graph, because what's going to happen is going to be a no calculator problem. This is going to be a somewhat complicated derivative. You're not going to know what that graph looks like. So let's recreate that same information that's down there, but without having a graph. So what we need to know is we need to know where f prime is positive or where it's negative, right? That's what I need. So we're going to do something called a sign analysis. Sometimes you'll hear me call this just do an f prime number line. Do a number line. Do a sign analysis or do an f prime number line. That's what we're going to do. So what I'm going to do is I'm going to write f prime. I'm going to make a little number line here. I'm going to put my 2 stationary points on it like that. Okay? Because what I need to know is I need to know where f prime is positive, and I need to know where f prime is negative, right? That's what I need to know. And if I know that, man, I got it whipped. Then I know where it's increasing, I know where it's decreasing, I know where its local max and mins are. So what I need to do is take some numbers here, like maybe a -1 and a 1 and maybe a 3, and I need to plug those into what? Because we're working with equations now, so we got to plug in. What do I plug them into? The f prime graph. Because what am I trying to find out? I'm trying to find out where f prime is positive, where f prime is negative. I already know where f prime is 0. That's what this gave me. So I know where f prime is 0, so I put those on there. Now, don't put little hash marks. It's amazing how much this little number line can get you in trouble. Don't put little hash marks here at the -1, 1, and 3. The only hash marks I want on my number line is that one and that one. And what I'm looking for is what is f prime in between here. So don't put little hash marks at those other ones. I just wrote those little numbers in that those are where I'm going to test, right? I'm going to test what is f prime over here, what is f prime in here. I can pick any number between 0 and 2. Okay, but don't put little hash marks there, but then it just gets totally confusing. All right, so I'm going to take, that's why I wrote these really tiny little numbers too. I don't want to confuse them with these two numbers. These are really important. Matter of fact, let me do this. There. Those are really important numbers. They're way bigger deal than those other little numbers I got. Okay, now we can take our -1 and we plug it in. Now I can either plug it in here, or I can plug it into my factored form. A lot of times I plug it into the factored form. Sometimes that's easy. So I'll put a -1 there, that's negative. -1 minus 2, that's negative. Negative times negative, positive. I don't care what it is. I don't care what value I get when I put in the -1. I only care if it's positive or negative. Now let's put a 1 in here. 3 times 1 is 1, or is 3, that's positive. 1 minus 2, negative. Positive times negative, negative. Now let's put a 3 in. 3 times 3, that's positive. 3 take away 2, positive. Do you see how this gives me the same information as that did? Gives me the same information. So we learned about it graphically, and we still need to know about that. But now here's how this would look with an equation. Okay? Well, there it is. I got everything I need. So, part A, where's the function increasing? Number 19 on page 121. A, where's the function increasing? Negative infinity to 0. 2 to infinity. B, where's the function decreasing? Between 0 and 2. C, where does f have local max min? I'm sorry. Where does the function have local max? X equals 0. Where does it have local min? Okay, now I'm going to make another comment here because I'm going to make a bigger deal about this tomorrow and next week too. Whenever we do a local max min, we didn't do it on this last quiz, but if I ask you where there's a local max or local min, probably going to ask you to justify that answer. Here's what the College Board says they need to see on the AP test. They need you, this is not enough justification right here. You've got to write this out. This is a local max because f prime changes, so you might jot this down, positive to negative, so f changes increasing to decreasing. You've got to make that f prime f connection of why that's a local max. So you got to have both parts of that thing. And then the same thing on part D.
Could you also skip the number line because it's 3x squared, so it has to be opening up, and therefore it has to be positive between
Since that's a simple f prime graph, and that's why I knew it did that. Once I found these stationary points, and I know this is a parabola opening up, and I know it's got to cross at 0 and 2, that's why I drew this little graph. Right, you don't have to have a sign graph, you have to have some evidence that this is what's happening. So on this particular problem, if you looked at that and said it's a parabola opening up, and you drew my little guy right here and put the plus minus plus, that's fine. That would be fine. That'd be in place of a sign graph. My warning to you is, most of the time when we do these equations, they're not going to be that simple, and you're not going to know what this graph looks like. And so therefore, this works all the time. Wherever it's equal to 0, put that on a number line, check some points in between, right? Plug those into f prime. Now, take that one step further. What if then they ask you questions about inflection points and concavity? What do you need to look at for concavity? F double prime. F double prime tells you about concavity. So what you would do is you would do then another step where you would do F double prime, set it equal to 0, and do a sign analysis on that. So if you had an F double prime number line with a number or 2 on it, and you plugged those into F double prime and you had positive, negative, positive, what's that tell you if F double prime goes positive, negative, positive? What's that tell you about F? Concave up, concave down, concave up, which would tell you those are inflection points because there's a change in concavity, right? So you would do this sign analysis on F double prime that would tell you about concavity and inflection points. Okay, so there we go. So we brought the chart now in together with this idea of the equations and those shortcuts that we learned with the derivative. Okay, and then the last step of that, and I'm not going to probably even hand that out. Yeah, I am too, but we won't do the whole. Well, no, I'm not. We'll do that tomorrow. Then the last step of that would be, then we can actually draw a graph of this pretty easily without a calculator. See, now this goes back to old school. We don't spend near as much time doing this as we used to because we had no good way of graphing something like this because we didn't have graphing calculators. We would go through all this and we would find out all this information, and it was a good way to then sketch that graph. We're going to do a little bit of that here. We're not going to spend much time on it. We're not going to really do a lot of that in the quiz. This part we still have to do, because this part applies to a lot of other areas of calculus. But the curve sketching, not so much. We're going to do a little bit of it. Because now what I can do is once I find my local maxes and mins, once I find my inflection points, once I find all that stuff, now I can just take those points and plug them back into the original, and then I can plot them, and that gives me a real good idea of where my graph goes. Okay? And it makes sense. It's a cubic, so it makes sense it's going to have a local max, and this can come down and have a local min. Okay? Makes sense if that's what's going on. Okay? So that's kind of tying all this together. All right, so your homework then, the next line on the assignment sheet says 3 through 12, number 21, which is just like number 19 that we just did here, and then also that calculator worksheet. I'll tell you what, I am going to give you this, and getting started on it's not a bad idea, because otherwise that's going to leave you more stuff for like Thanksgiving homework, and I don't want to give you a whole bunch of that. So I'm hoping to give you more work time tomorrow, okay? So I'm going to give you this, and you can begin to look at just the first page of it, but you don't have to go through it yet. Okay, like the first page. Matter of fact, to be honest, on this new little packet I gave you, probably the front and back of the first page would be the part I would wait on. I would wait on that part. The other problems are actually a little bit easier. They just have you, they give you information, kind of chart information, and they have you just sketch little graphs. So depending on what your schedule's like, because I know tomorrow night, if you're going to the game and everything, and then you got Thanksgiving, right? So if tonight's the night where you can get a little more done, maybe you can do a little bit of that. But this will be done, kind of due next Monday. So
Just get started on it.
you can get started on it. The first 2 pages, I would say, though, I wouldn't do those. The back pages are actually easier for right now. Okay, because the book problems aren't going to take you very long. That 3 through 12 and some chart stuff, that's going to take you 5 minutes. Number 21 is like this problem, so it'll take you a little bit longer. And then that worksheet's not going to take you. So this isn't a whole lot. So getting going on this worksheet wouldn't be a bad idea. No, I'm going to change my mind.
That was just this and this